Hi, welcome back. It's the first actual lab where we're going to try to actually learn something here. It's a little strange because doing this from home, I don't have the shop and I don't have all the equipment that I'd necessarily like to have. When we do things in person, it'll be obviously a little bit better. But this is kind of a short thing. We'll be back soon, early February. So um, it is what it is. I have a little kind of demonstration about electricity. We start the semester by talking about the nature of electricity and a little review of electricity and things like that. So uh, when we talk about electricity for like lighting systems and um, motors and stuff like that, we're concerned about current flow and we're concerned about electrical power and stuff like that. When we're doing computers, we're not so much concerned about that. We are more concerned about um, voltage and using voltage levels as a form of information. So what I intend to show you today is, first we're going to look at some different voltage levels, and we will look at what they do as far as current flow, what that relationship is between voltage and current flow. And we'll look at how resistance, a couple different, resistances and how that affects current flow. But then we're going to move on to worrying more about something called voltage drop. You should have heard of it if you took electrical class, so it won't be brand new to you. But the concept of voltage drop is, when current flows through a resistance, voltage drop happens. So I have a couple demos to show you what voltage drop is, and then one or two things that just talk about how that's used in different kinds of sensors in order to provide information by varying levels of voltage. So we'll get to that, and then I'll come back and kind of wrap up when we're done. So let's start with the first topic, voltage. I have the meter lead set up for volts here, and I'm going to turn it to DC volts. And as you can see, I have a couple of different batteries sitting here on the bench top, and I just want to measure each one. This is a AA, and if we look at that, if I can get a good hold on it, yeah, we see we have a little over 1.5 volts. In fact, if I put two of these end to end, oops, I had it for a second. We have about 3.25. So what we're seeing here is two batteries in series. I have positive of one to the negative of another. It's used a lot of times in small appliances where it uses 2, 3, 4 AA batteries in order to get 3 volts or 4.5 or 6 volts. Here's a C battery. You don't see these too often anymore, but it's bigger, but this one must be kind of dead. It's supposed to be about 1.5 volts as well. So these two batteries have the same voltage. The difference is this one can supply power for longer because it's bigger. This one here we all know is a 9-volt battery, and if I look at that, we can see our voltage is about 9.5 almost. So we have a couple different choices for a power supply. So what difference does this make? Well, voltage is kind of like the potential for pushing current. Kind of like having a car with a 700 horsepower engine. It has a lot of potential for going fast, but that potential is not necessarily used all the time. So in an electrical circuit, I may have high voltage, but if I don't have a pathway or let that voltage flow, then I'm not going to get a whole lot of current. Just like in the car, if I don't let air in, if I don't open that throttle, I'm not going to get a whole lot of power out of it, even though I have the potential there. So these batteries represent electrical potential, which is another name for voltage. Let's see if we put one of these to work. So I have here a 3157 light bulb. And I'll just use a couple jumper wires here. Give me a minute. Okay. So I'll just hook one jumper wire to each side of this bulb. And we'll try hooking it to some of these different voltage sources. So let's do the AA, which we know is about 1.5 volts. Well, I can see, and I don't know if you can, well obviously you can't with the way I have it there, a very, very dim glow on the one filament. Probably not even enough for the camera to pick up. 1.5 volts, not pushing a lot of current through that light bulb. Let's go with the 9 volt. Yeah. Sorry. Batteries aren't really made for these jumper clips so much. With the 9 volt, the light's definitely on and glowing. What's the difference? So 1.5 volts just can't push enough current through that light to light it up. The 9 volt was able to. I have here, move these a minute. I have here a power supply, and this power supply is able to put out significantly more voltage. Let's just see here. I turn this on. That's about 13.5 volts almost. 13.45 I think it says. 13.45. Alright, so let me move these batteries aside for a minute. And let's see what happens with this light bulb if I hook it to that higher voltage. We saw it at 1.5 volts, roughly. We saw it at 9 volts. At 13.5, I can't even really look at it. So what have we just seen? We've just seen that higher voltage results in a brighter light. So this is about 13.5 volts, giving us the brightest light that we've seen so far. So what's going on here? We can actually measure that. And for that, I have to set up the meter to a different setting. I'm going to switch it over to DC amps. In order to do that, we also need to move this meter lead over to the 10 amp spot. We'll switch our meter to DC amps, and now what that allows us to do is run the current through the ammeter and through the light bulb. So here's how we're going to hook it up. From the power supply, we're going to go to one of our meter leads right here. That second meter lead now becomes our power supply. Just untangle this a little bit. And we can run that into the light bulb. So if I touch it, our light comes on. Let me hook that up a little bit more permanently here so I don't have to hold it. We'll just take another jumper wire and clip that in place. Now, it's going to be a little bright to stare at, but there we have the light bulb. I'll move it off to the side a little bit. Kind of cover it up so we can look at the ammeter. Here it tells us we have 2 point, that may be too bright here. Put this down somewhere else, I guess. 2.72 amps off of this light bulb. Turn that off a minute, and now we're going to try to go back to the 9-volt battery, which we know didn't give us as bright of a light. Let's see if that affects the current flow on this thing. Okay, right now with the 9-volt, looks like we have, I don't know if you can see that, about 1.25, about 1.25 amps. We'll unhook that in a minute. And if we go with the AA, I don't know if you'll even be able to see the meter, but the AA gives us about 0.9, and there's the tiniest little glow coming from the light bulb. It says 0.90 right now. Okay, so what we've seen is not only does the voltage we apply to this load affect how bright this light bulb is, but it affects the current flow through it. And that's no coincidence. In other words, I guess what I'm saying is current flow is what makes the light light. So more current flow causes more light. So what I'm going to do now is look at another thing that affects our current flow, and that's resistance. So I have to switch our leads back, and I'm going to set our meter to the ohms position, and that allows us to check resistance on things. So the leads have about 0.1. Let's check the resistance on this light bulb, and it is hang on, I'll just use the jumper wires to do it. About 0.8 ohms. So when we use the power supply, let's do it again, right? So we'll use the ammeter, because I don't remember the number we came up with. And we'll feed our power supply into the ammeter. And we'll use our other lead here to power up the light bulb. Okay, it was about 2.17. Okay, 2.17 amps we got there. Take a different light bulb here. This one is smaller. That doesn't necessarily mean that the resistance is less. Let's actually measure it. Too hard to hold the leads right on the bulb, so I'm going to use these jumper wires for it. So the resistance on this, 4.7 ohms. So we had less than 1 ohm on the bigger light bulb here, and this is about 4.7. So what do you think that's going to do to our current flow? We can measure that and find out. So again, back to our amps. And we'll start with feeding power into our meter right here. Our light bulb will be hooked to ground. And our other meter lead is now our hot. Oh, I see it looks like about 0.01 amps. And with this bulb, we had 2 1/4. This bulb has to be burned out. Let me grab a different one here. I do have another. About 1/4 of an amp. So the bulb lights about 1/4 of an amp. It's not quite as bright as that other bulb, but why is the current different on those two bulbs? Obvious answer, the resistance is different in them. So that bulb that has the lower resistance has more current flowing through it when we hook it up to the same exact power supply. This was about 13.5 volts on this power supply here, if you remember. We had less than 1 ohm of resistance here. We got 2 1/4 amps, 2.17. Here we had almost 5 ohms of resistance, and we had a much smaller current flow. So now let's see what happens when we combine more than one load in a circuit in series, because when we're talking about computer assisted mechanisms, very often our sensor circuits are actually series circuits. And so we're going to look at something called voltage drop. Now, rather than get crazy with the meter, we've already seen that the brightness of the light bulb is tied pretty much directly to how much current is flowing through it. When we had our 9 volt, the current was a lot less than the 13.5 volts that the power supply here provides. And we saw that in the brightness of the bulb. So if you see a brighter bulb, you can bet there's more current flowing. So let's look here with just one, and this does screw up the camera, my apologies, but the bright light, the camera automatically tries to adjust. But one bulb, as we know, very bright. Turn that out and see if our camera can recover. What I'm going to do now is I'm going to hook 2 bulbs in series. And they're identical bulbs, so we're going from one to the other. And what we see here, you can almost stand to look. Whoops, you can almost stand to look at these. They're not quite as bright. So what's happening there is, because they're in series, the resistance of this bulb is combined with the resistance of this bulb, increasing the total resistance in the circuit and slowing down the current flow, or reducing the current flow is actually a more accurate statement. If I add yet another bulb in, see if we can do that. This one is a little different. So from that bulb going to this bulb now, and back to ground. Now we have 3 bulbs lit, but they are all significantly dimmer than what we had. Hard to see that other one. I keep shorting these out, sorry. Three bulbs, not as bright. If I look at the current now, with one bulb we noticed we had, I think it was 2.17 amps. If I go and measure the current now, so we'll snag our power and put it through our meter. These are touching, hang on. Okay, 3 bulbs. There we go, finally got a good connection. About 1.3 amps. So we went from about 2 1/4 to about 1 1/4 when we put 3 bulbs in series. So more interestingly, what's happening to the voltage here? That's something I want to look at. So let's get everything hooked back up so our lights are all lit. Right. And I'm going to hook my negative meter lead here to our ground terminal. And we'll go to DC volts, and I'll take my positive, my red meter lead, and I'm going to start at the power supply. See that I have about 13.4 volts. If I follow this wire down to where the first bulb is, before that bulb, still about 13.4. On the other side of that bulb, we're down to about 8.38. Now I follow that wire to the next bulb, 8.29, but on the other side of that bulb, about 3.2. And then if I follow that wire to the next bulb, we have most of that 3.2, but on the back side of that, we are down very close to 0, 0.016. So we're almost back to ground, and that's almost what we're reading. If we get all the way back to ground, then we obviously have 0. So what we call this phenomenon here is voltage drop. We start with a voltage level 13.5 roughly, and then as it goes through each bulb, some of that voltage is dropped. There's after 1 bulb, there's after 2 bulbs, and there's after 3 bulbs. If I only put 2 bulbs in this setup here, so you take this this last one out of here, the first one out of here, I guess. This might even be a little simpler to watch. So here we go from our positive connection to bulb number 1, then to bulb number 2, and then back to ground. So I gotta bring some light up to this meter here. So if we start at our battery positive, right, battery positive, we have 13.5. We follow that after the first bulb, we're down to about 6.7. And then after the last bulb, of course, we're very close to 0. Turn that off. Give our camera a chance to recover here. So what's happened here is, like I say, a phenomenon we call voltage drop. And this is what occurs when you have a series circuit. And like I said, this is going to be really important for understanding how certain sensors work. If you have a series circuit, the voltage you provide to it, in this case about 13.5, is divided among those loads. So when we put 3 bulbs in, it split it. First bulb lost some voltage, second bulb lost some more voltage, third bulb lost pretty much the rest of it. When we put just 2 identical bulbs in series here, we started out with 13.5. We were down to about half of that in between the 2 bulbs. So first bulb dropped half the voltage, second bulb dropped the other half. So that was pretty easy to see or figure out. Let me get rid of these light bulbs for a second. Take all that down. And here, in their place, I have a couple of resistors. So the resistors, the advantage here is that they will allow us to measure resistance and voltage drop without lighting up and screwing up the camera. So the first thing I want to do is measure the resistance of each one. So we're going to put this on ohms. I'll use these little jumper wires here to extend my meter leads, just makes them easier. So we'll hook to one side of that resistor. And then to the other side of the resistor. And it's kind of hard to see here, but it says 102, but it's 102 k ohms. You got to look really closely to see that it's so 102,000 ohms. This other one here is about, that says 32.9 k. So that's 100. This is a 33, essentially. As you can see, I've connected the two resistors end to end, in other words, in series. And looking at the combined resistance, about 135.5 k, which is in keeping with the one. The one was 102 k, and the other was just about 33 k. So, as you know, when you put resistances in series like this, the resistances add up. So that's the resistance. What I'd like to look at now is current flow. So let's first start by just simply hooking to our power supply here. And I'll turn the power supply on, and nothing much going on here. So let me set the meter up for amps. And we'll run our power out of the power supply into our ammeter. And then from our ammeter into the circuit. See what we get. Yeah, very, very tiny. As you might expect, we have 13.5 volts. We have something like 135,000 ohms of resistance. So I didn't really expect to see any current flow. So this circuit, the way it is, there's not enough current flowing through this to do any kind of work at all. It's not going to light a light bulb or spin a motor or anything like that. However, this still, a series circuit like this, resistance in series, still has some use for us. So let me turn this off, unhook things, and let's see, take the meter out of here, right? So we are just powering up the circuit like it was before. So there's our two resistors. And I'm going to put this meter to volts. Right, so DC volts right here. Hook my black meter lead to ground. So now the red meter lead will measure voltage, right? If we go to the power supply, we get to 13.45. Right? So following that wire from the power supply, before we go into the first resistor, we still have the 13.45. At the other end, we're down to 10.15. So we dropped a little over 3 volts. This is, voltage drop from 13.45 down to 10.15. So this must be the smaller resistor. This must be the 33 k ohm one, because it's only dropping, about a third of the voltage. This one over here, on the other hand, it goes from 10.15 down to pretty much 0, so it's dropping 10.15 volts, which is much more than the drop we got on this one. So this must be the 100 k ohm resistor. We can also measure that directly. In other words, instead of hooking the meter to ground, I can measure right across that. This resistor, 3.26. This resistor, 10.15. So we're able to see the, let me turn that a little more for you. we're able to see the voltage drop that happens over each resistor, and it's proportional to the resistance. You know, the bigger resistor gave us the bigger voltage drop. And when I say bigger, I don't mean physically larger, I mean 100 k ohm as opposed to 33 k ohm. So that kind of sets us up for the next thing we're going to look at, which is a type of sensor that uses voltage drop as a form of information to feed the computer information about the position of something on the vehicle. Now I want to do a little bit of an experiment. And the experiment, the idea is to show you how certain types of sensors work. And this is really kind of simple, but it's kind of neat in the way that it works. So what I have here, regular piece of paper. I have a number 2 pencil and some paper clips along with my meter, of course. And I'm just going to start by doing a little bit of scribbling with my pencil on this piece of paper. So I'm drawing a line, trying to make it a pretty heavy black line. And you might know already, but pencil lead isn't really lead. What it is graphite. And graphite can conduct electricity. Let me set this to ohms and see if there's any continuity here on my little pencil line. So right now, yeah, we're seeing actually looks like about 10.8 megohms on that pencil line. What I want to do now is make that line a little bit thicker and darker if I can. See if that has any effect on it. I'm trying to keep this relatively square and sort of neat. Art was never really my thing, but so here we go. Here's a little bit thicker line. Take my ohm meter again, and we'll see. Yeah, that's down to about 3.7 megohms. So what you can see here is that, you know, if I lay down more of this graphite, we're going to have a better conductivity. Interestingly, years ago, there was an electronics manufacturer in the local area that had a workforce that knew how to operate the machines, knew how to make the electronic components, but they really had no idea how these things worked. And so they asked us to run some classes in basic electrical and electronics so that the people making these devices, and there were ignition modules, there were different sensors, the people making them would have some idea what it was they were making and how they actually work. It was a kind of a not really necessary training. They didn't need to know this in order to make the devices work, but you know, the company was a little progressive. They wanted a more educated workforce, a smarter workforce. So one thing that I learned when I saw their processes is they had some resistors inside some of their circuits that were not resistors like you've seen these things. This is a resistor here, right? But the resistors were actually conductive ink that was printed onto the circuit. So kind of like I have just put this conductive graphite onto this paper, they were printing resistors out of special ink. And to adjust the resistors, to get the resistance level exactly where they wanted them, they were controlling the width of that printing. So they would actually hook a circuit to it, check the voltage drop of that resistor, and then they would trim the resistor with a laser. So it would actually cut into the material and open up some of the path until their voltage drop was exactly where they wanted it, meaning their resistance was right where they wanted it to be. It was really pretty interesting. So I think I have enough graphite laid down here. It's important, you know, if this experiment's going to work right, that it's kind of uniform. So I just want to go over it a little bit. That's probably pretty good. So let's take the meter And let's start way out on the outer ends here and see that, on the outer ends I've got about 0.7 megohms. And if I slide these closer to each other, what I notice now, that's 0.38 megohms. Here, 240 k ohms. There are some gaps in here, so it's not perfect. When they're really close together, I've only got 76 k ohms. So the resistance I'm reading has a lot to do with how far apart these meter leads are. So now I'm going to do something a little strange. Let me just move these paper clips a second. I'm going to hook my piece of paper up to my power supply, which is about 13.5 volts. So there's my piece of paper connected to the power supply, and I'm going to turn on the power supply. Obviously nothing happens. We don't have any light glowing out of it or anything like that. But I want to use this resistor that I've just created, and we'll call it a variable resistor. And I'm going to switch my meter to volts, and I'll ground the black lead. Let me just get a wire here. Just hook the black lead to ground. Right. There we go. So now my meter has a ground. And take the red lead, and we'll go to our power supply. We've got the 13.45 volts. And down at our connection, we've got 13, just about, the same 13.45 almost. At the ground side, over here, we've got 0 volts. So up here, 13.5, here's 0. That's connected to our ground, which of course would be 0, right? What do you think if I put my voltmeter lead right in the middle here? I've got 6.42 volts. That's about half. If I put it up here, closer to the positive one, I've got 9.8. If I put it down here, closer to the negative one, I've only got 2.39. Excuse me. A little dust. I don't know if I'm going to edit that out or not. So to make this a little easier, so I'm not holding this meter lead with my hand, I'm going to hook it up to another jumper wire and a paper clip. So let me put that paper clip on my piece of paper here, hook my meter lead to it. Whoops. It's a little heavy here, so there we go. The meter lead is hooked to it. And we're about in the middle of this resistor, and we're seeing about 6 volts, which is, about half of the total voltage here. So I'm going to now slide it closer to the positive terminal. So we'll just slide it up there. And now it's up to 9 volts, right? And if I slide it a little further, now we're up to 10.75. What's happening here? The closer we get to our source voltage here, the higher our voltage reading is. And the closer we get to our ground down here, the lower our voltage reading is. Using this, we can actually make kind of a position sensor out of this, right? So let's call this 0%, call this 100%, and call this right here 50%. So if I'm designing this system and I'm writing the software that's using this sensor, I'm going to know that if my computer sees on the wire coming from this sensor 6.13 volts, that my sensor is right at 50%. It's right in the middle of its travel. we can say, you know, let's make this 60, 70, 80, 90%, and going the other way, we'll go 40, 30, 20, and 10. If I just have a chart that tells me that 40% equals 4.9 volts and 30% equals 4.2 volts and 20% equals 2.2 volts and so on, then I can know, without looking at this, right, I can know exactly where my sensor is. So I could cover this, right, and we see 9.43 volts. We know we're somewhere more than half and not all the way to 100%. So we're at about 70% here. So this is a position sensor called a potentiometer, and they are used all over the car anytime we're trying to measure the position of something. So some examples would be accelerator pedal position or throttle position, positions of doors and HVAC systems. And so it's a very simple 3-wire sensor. And the 3 wires, this is important, right? There's the reference voltage. In our case, it's 13.45. There's the sensor ground, and then there's the signal wire. And the signal wire is the one that changes, right? As the sensor moves, the voltage on that signal wire is what's changing. The voltage on our reference voltage and ground wires doesn't change at all. That remains constant. Something I should tell you, I'm using a 13.5 volt supply in a car using a real sensor. It's a 5 volt supply. So reference voltage is 5 volts. I do want to point out what happens if there's a fault. We're talking about the normal reference voltage being 5 volts. So what happens if there's a broken wire or if the sensor goes bad? It depends on which wire breaks, but if the ground wire gets disconnected, instead of our 6.18 volts that we're reading from being right around 50%, if I disconnect this ground, you can see we go up almost to our full source voltage. Without that ground to cause the voltage drop, we're measuring essentially what we have here. If on the other hand, if the reference voltage wire becomes disconnected, we see almost 0. And the same thing if our signal wire becomes disconnected, we see almost 0. So what is normal? What's expected? Sorry, this is not the highest quality potentiometer, so things aren't perfect, but what's expected is that the reading is going to be somewhere between 0 and full reference voltage, but it will never be either one of those. So if it sees 0 volts, it assumes that one of these 2 wires has become disconnected, or the sensor is open circuited or something. If it sees full reference voltage, then it assumes that there's a problem with this ground wire or something has happened with the sensor. So the normal range for most of these types of sensors is somewhere between about 0.5 volt and 4.5 volts. So if the computer sees 0, it's a problem. If it sees 5, it's a problem. There's a range that's considered normal. And like I say, that's, in some cars, it's, in some sensors, 1 volt would be the low end of it. Let's take a throttle position sensor. Closed throttle, depending on the car, might be 0.5 volt. It might be 1 volt. Wide open throttle is probably going to be about 4.5. If it sees 5, that's no good. Something's wrong, and it will flag that as a diagnostic trouble code for that sensor. So that kind of wraps up the demo for today. Sorry, sometimes it's hard to get a good camera angle. It's hard to get the right lighting, and you know, it's hard to maybe follow along. It's not as good as in person, but we do what we can. So after you've watched this, you've all done lab reports. None of you should be brand new students. So I need you when we show up, so it should be next week. Oh no, email it to me. Email me a lab report. Right now, it's you're watching this, it's probably Monday, so whatever day you have lab, if you're in the Monday lab or if you're in the Tuesday lab or the Thursday night, by the following week, I expect to have that lab report. Those are the rules. You know, you have a lab 1 week, you give me a lab report the following week. I think for most of us, this is the only online lab we'll have to do, and then we'll be, you know, in school after that. So then it'll just be normal, do the labs, hand me the lab report the following week. So watch the video, write me a lab report. Obviously, you're not going to be able to put down any vehicle information, but I need you to tell me what you saw. And so I know that you watched the whole thing and that you understood it. If you have questions, obviously send them to me by email, and then we can talk about things even further when I see you in person. So, about to go watch the Bills game pretty soon. It's Sunday. It's around 5 o'clock. So we'll see what happens with that.